Today's lesson is 2.2.1, three-angle measure, and it's an introduction to trigonometry. So our learning goals today are going to be exploring trig ratios as measurement conversions and analyzing the properties of similar right triangles. So we're not going to really get into trig completely. We're still kind of brushing the surface, and some of the stuff that we talk about today will be things that you've already seen before. So you know about the proportionality between side lengths of similar figures. What is the relationship between the ratios of the side lengths? So we've been pretty familiar, well, I shouldn't say familiar, but we've been exposed to 45, 45, 90 triangles, and you'll see that both angles are 45 degrees, and then since it's a right triangle, obviously the third angle is 90 degrees. So question 1 in this lesson is choose any point along the hypotenuse of triangle ABC and label it point D. Then construct a vertical line segment DE connecting with side AC so that DE is perpendicular to AC, and then label the other endpoints as E. So I'll go ahead and do that now, and then you can copy that into your workbook. All right, so explain how you know that triangle ADE is similar to triangle ABC. Well, they both have 90-degree angles. They both have 45-degree angles. So therefore, they must be similar by angle-angle similarity. You know that the hypotenuse of a right triangle is the side that is opposite the right angle from last class. In trig, the legs of a right triangle are often referred to as opposite side and adjacent side. So this is something we went over last class. These references are based on the angle of the triangle that you're considering, and we will actually call that a reference angle. So that is something new. So that's a new vocabulary word. And then here is a picture that you can use to kind of make sense of these vocab words. All right, so, and again, if you guys are following along in the workbook, which I hope you are, we are on page M2-124 at this point, at the top. All right, so you can just watch here and pause to get this into your workbook. We do not have to actually do the calculations. So it says record the side length measurements for both triangles in the table. And I should say, I'm going to do the calculations, not you. You can go ahead and just copy it in. So if we're using A as our reference angle, then the opposite leg is going to be 4.9. So I measured that for you, and you can put that into the table. The next thing is DE. It's still opposite A, and it's 2.3. Obviously, it's going to be less than 4.9. Put that in the table. And then the adjacent leg of the large triangle and the adjacent leg of the smaller triangle will be 4.9 and 2.3. And it makes sense because this is a 45, 45, 90 triangle, which means it's an isosceles triangle. And then the hypotenuse of the large triangle is 6.93 if you add those two segments together. And then the smaller one is 3.25. So determine each side length ratio using angle A as the reference angle. So we're now putting these into ratios. So I will fill in this table, pause, and then fill your table in as well. So let's analyze the recorded measurements. Compare the side length ratios of the triangles from your table. What do you notice? So look at your table. What are you noticing? Obviously, hopefully we all notice that we've got the same ratios when we have the opposite over hypotenuse, and the same ratios when we have adjacent over hypotenuse, and then the same ratios when we have opposite over adjacent. So you've estimated certain constant ratios of side lengths of 45, 45, 90 triangles. You can use what you know about this, and this would be the triangle theorem, the 45, 45, 90 triangle theorem to determine exact ratios. So we are on page 127 at this point. So question 10 says, given a leg length x, determine the lengths of the other sides of the 45, 45, 90 triangle. So we don't have an actual value of the side length. We're going to use x instead. And so all the other side lengths will probably contain x as well. So if they're both 45, 45, 90, then I know my two legs are the same length. So x and x. And then from there, if we use Pythagorean theorem, we will quickly figure out that x is, or the hypotenuse, is radical 2 times x. So go ahead, pause, get that into your notes. Number 11, determine the ratio of, first, the opposite side length to the length of the hypotenuse. So we're going to set up ratios here. I'm going to go through this, and then you can go ahead and pause your notes and get this into your workbook. All right. Next one, we're going to work with adjacent side lengths. So if you see, I'm going to go backwards. X over radical 2 times x, that's opposite over hypotenuse. And then you'll see too why it looks like it doesn't change when you go to part B, because our adjacent side is also x, so it will be the exact same. So go ahead and pause, put this in your workbook. And now this one's a little different. Opposite side over the adjacent side. Well, that's just x over x, so that would equal 1. All right, so determine the unknown side length. So it looks like we've got two triangles here. The hypotenuse is 60. It's a 45, 45, 90. So both legs are x. So we're going to work backwards. If we know that the hypotenuse, or if we know that the legs are usually radical 2 over 2, so the ratio of opposite over hypotenuse is x over 60. We know that would eventually reduce to radical 2 over 2, so we can cross multiply. And we will get radical, or 30 radical 2. All right, moving on. Ratios in 30, 60, 90 triangles. So this is activity 1.2. This is on page 128. So again, we've been exposed to 30, 60, 90 triangles. So we've got this 30, 60, 90. Question 1. Choose any point along the hypotenuse of triangle PQR and label it point D. Then construct a vertical line segment DE connecting with side PR so that DE is perpendicular to PR. Label the other endpoints as point E. So again, so I've just drawn it there. You can pause and draw it as well. I'm going to measure all of these for you and fill in the table for you, so you'll want to pause and do that too. So if P is my reference angle, then I'm going to find all of these measurements, throw them into the table, pause here, copy it in. Now we're going to throw the ratios into the table. Pause here and write that in somewhere into the second table on that page. And then what do we notice? Same thing, opposite over hypotenuse is the same. Adjacent over hypotenuse is the same. And the opposite leg over the adjacent leg is the same. So just like a 45, 45, 90. So what conclusion can you draw about the three ratios you studied in both the 45, 45, 90 and the 30, 60, 90? For each kind of triangle, the side length ratios are the same no matter the size. Question 6, what conclusions can you draw about these three ratios for any right triangles with congruent reference angles? Explain your reasoning. So let's just chat about that. Any right triangles with congruent reference angles, if the reference angles are the same, then we know their ratios are going to be the same. And then question 8, let's see what page we're on. We are on page 129. So is each of the three ratios you studied in this lesson the same for any triangles with congruent reference angles? So this would be a no. The triangles must be right triangles, and the triangles must be similar. So they have to be right triangles, and they have to be similar. Question 9, page 130. Given a length of the shortest side, x, determine the lengths of the other sides of the 30, 60, 90 triangle. So we did this a little bit with the 45, 45, 90 as well. So we've got 2x, we've got a long leg, and we've got a short leg. And this is something we learned about last class. So we're trying to find x here. So we're going to use Pythagorean theorem. Go ahead and pause, and you can write this into your notes. And we eventually get that we're not trying to find x, we're trying to find the long leg. And we get that the long leg is radical 3 times x. Pause, get this into your workbook on question 9. So question 10, this is the last one. Determine the ratio of the opposite side length to the length of the hypotenuse. So opposite over hypotenuse would give you 1/2. And then let's do the adjacent. Adjacent side over hypotenuse, radical 3 times x over 2x. That would give you radical 3 over 2. And then determine the opposite side length to the adjacent. We've got x over radical 3 times x. So simplify that, rationalize the denominator, and we get radical 3 over 3. So pause and get that into your workbook. So the three ratios you worked with in this lesson are very important to trigonometry and have special names and properties. You'll learn more about these ratios in the next several lessons.